Today, we're going to dive into a state of matter that is so bizarre it almost seems to defy the very laws of physics. We're going on a journey to the absolute coldest temperatures possible in the universe to find a quantum phenomenon that's actually changing how we see the world. So, let's get into it.
All right, I've got a riddle for you to start us off. What's like a strange fog, made completely of atoms? But, and here's the wild part, even though there are millions of these atoms, the whole cloud moves and behaves like it's one single giant object. Any ideas?
Well, the answer is a Bose-Einstein condensate, or BEC for short. And yeah, it's the fifth state of matter, right up there with solids, liquids, gases, and plasma. The reason you probably didn't hear about this one in your high school science class is that it's a pretty recent discovery from the world of experimental physics. You can't just, whip one of these up in a lab beaker.
Okay, to really wrap our heads around what a Beck is, let's use an analogy that I think we can all picture pretty clearly. A crowd of people.
Think about an ordinary gas. It's like a chaotic crowd in a subway station during rush hour, right? Everyone's bumping around, moving randomly, each person with their own speed and heading in their own direction. Now, a Bose-Einstein condensate, it's like that same crowd suddenly starts moving in perfect, synchronized harmony, almost like they've all become a single unified being. All that chaos just vanishes, and what's left is this incredible collective order.
So how in the world you get this unruly crowd of atoms to act in perfect unison? Well, you cool it down. And I don't mean just freezer cold. We're talking about cooling it to almost absolute zero. That's minus 273.15 degrees Celsius, the coldest temperature that is physically possible in the entire universe.
And you might be thinking, wait a second, if you make something that cold, why doesn't it just freeze into a solid block? That's a great question. And the answer takes us into the very strange world of quantum physics. See, at these ridiculously low temperatures, our everyday logic just stops working. The rules of quantum mechanics completely take over. And the most important rule here is this. Every particle, including an atom, isn't just a tiny little ball. It's also a wave. Here's a cool way to picture it. In a warm gas, think of each atom as an individual wearing its own tiny little wave coat. As you start cooling the atoms down, they slow down and their wave coats begin to expand, getting bigger and bigger. Eventually, you get them so cold and slow that these wave coats start to overlap and then just merge. The whole collection of atoms is now described by one single shared quantum wave. They've literally lost their individual identities and started behaving as one giant superatom.
Now, this might all sound like something straight out of science fiction, but the idea of a BEC was actually predicted way before anyone could possibly create one. In fact, it took a 70-year journey just to turn the theory into reality.
It all started back in the 1920s. Two brilliant physicists, Satyendra Bose and the one and only Albert Einstein, they asked this groundbreaking question. They basically said, what if? What if you could take a special type of particle and cool it down so much that every single one of them collapses into the exact same lowest possible energy state?
And those special particles they were talking about, they're called bosons. The easiest way to think about them is that they're very social particles. They have absolutely no problem sharing the same quantum state. It's like they're all happy to pile into the same quantum chair together. In fact, the particles of light, photons, are bosons, which is why you can have an incredibly powerful laser beam with all those light particles packed together perfectly. So for decades, this incredible idea was just stuck on paper. It was a beautiful theory, but that's all it was. The problem was technology. Nobody had a clue how to get a gas cold enough to make this happen without it just, turning into a boring old solid. The big breakthrough came from a technique called laser cooling. And I know what you're thinking. How can light make something colder? Well, picture an atom just zipping through space. If you hit it head-on with photons from a laser that's tuned just right, each little impact acts like a brake. It slows the atoms down. And since temperature is really just a measure of how fast atoms are moving, slowing them down is the exact same thing as cooling them off. And this all leads to this incredible moment in 1995. In a lab in Colorado, scientists finally pulled it off. On their monitor, they first saw this blurry patch of light, just a warm cloud of rubidium atoms. But as they started the laser cooling process, something amazing happened. A sharp, intensely bright spike suddenly appeared right in the middle of that cloud. And that peak, that was the proof. Millions of individual atoms had merged into a single quantum state. The Bose-Einstein condensate was real. This timeline really shows you the incredible journey this idea went on. from a wild theory back in 1924 to finally being created in a lab in 1995. And then, in 2001, Eric Cornell, Carl Wieman, and Wolfgang Ketterle were awarded the Nobel Prize in Physics for their amazing work.
So this is all fascinating stuff, for sure. But you might be asking yourself, okay, but what's the point? Why does creating this super cold, exotic thing actually matter in the real world?
Well, a BEC is way more than just a scientific curiosity. It's an incredibly powerful tool. Because all the atoms act as one single quantum wave, the entire cloud is exquisitely sensitive to outside forces. I mean, a tiny, tiny nudge from gravity causes the entire wave to shift in a way we can actually measure. This lets us build ultra-precise sensors for things like navigating without GPS or even finding natural resources deep underground. And we can use them as quantum simulators. Think of it like a quantum sandbox, where we can model complex systems that are impossible for even our best supercomputers to handle, helping us design new materials or even understand what the early universe was like.
So really, when you boil it all down, this fifth state of matter is two things at once. It's a window, letting us peek into the fundamental rules of quantum physics, and it's a tool, one that's helping us build the technologies of the future. It's just a stunning example of how quantum laws can take a chaotic gas and transform it into a single, perfectly coherent wave of matter.
And that brings us right back to our final question. We've seen the incredible things that happen when you cool atoms down this far, but the whole thing hinges on that one totally bizarre idea: laser cooling. How on earth can a beam of light, something we always associate with heat, be used to create the coldest temperatures in the entire universe? Well, that's exactly what we're going to explore in our next explainer.